Good evening and welcome to the Obscura Institute. The lamps are lit, the archive is open, and tonight we draw a single file down from the shelves. File 4, The Mystery of Tabby's Star. Settle in, make yourself comfortable, and let us begin. 1,500 light-years from here, in the constellation Cygnus, there is a star that does not look like much. You could not find it with your eyes alone. It sits at around magnitude 11, which means you would need a telescope to see it at all. And even then, it would be one faint point among thousands. It is a little larger and a little hotter than our Sun, an ordinary working star of a common type, the sort that astronomers call an F-class main sequence star. In every catalogue, it is just a number, KIC 8462852. A Kepler input catalogue number, assigned because the star fell within the patch of sky that NASA's Kepler Space Telescope had been built to watch. And watch it did. Between 2009 and 2013, Kepler stared at a single field of the sky without looking away. It was monitoring more than 150,000 stars at once, measuring the brightness of each one again and again, looking for the faint regular dip that happens when a planet crosses in front of its star. A planet passing between us and its sun blocks a tiny sliver of light. The star dims by a fraction of a percent, then recovers, then dims again on the next orbit. Tidy and predictable, and repeating. That was the whole idea. Find the rhythm, and you have found a world. KIC 8462852 had no such rhythm. Its dimmings were deep and ragged, and they did not repeat. And the people who first noticed this were not professional astronomers at all. They were volunteers. Kepler produced far more data than any team could examine by eye, so the scientists running it opened the archive to the public through a project called Planet Hunters, part of the Zooniverse, where ordinary people could log in from home and look at the light curves, the simple graphs of a star's brightness over time, and flag anything that looked strange to a human eye. Computers are good at finding regular patterns. They are not so good at noticing the genuinely odd thing that fits no pattern at all. People are better at that. And starting around 2011, the people looking at this particular star kept stopping. Something here was not right. The dips were too deep, and the shapes were wrong. One volunteer after another tagged it as bizarre, interesting, unlike anything else in the field. They flagged it, discussed it, and would not let it go. The volunteers' notes found their way to a young astronomer named Tabitha Boyajian, then a postdoctoral researcher at Yale. She took the strange star seriously. Over the next few years, she and her colleagues gathered everything they could about it, checked the data for errors, ruled out the boring explanations one by one, and tried to make sense of a light curve that refused to behave. The result was a paper published in 2016 in the monthly notices of the Royal Astronomical Society, with a title that tells you something about the spirit of the thing. It was called Planet Hunters 9, KIC 8462852. Where's the flux? Flux is the astronomer's word for the amount of light arriving from the star. Where's the flux? Where did the light go? Among themselves, the team had taken to calling it the WTF star, a joke folded neatly into the question. Several of the Planet Hunters volunteers who had first noticed the star are named as co-authors on that paper. They earned it. The catalogue number was a mouthful, so people did what people always do. They gave it a name. KIC 8462852 became Tabby's star, or Boyajian's star, and Boyajian herself in time moved on to Louisiana State University, with the strangest star in the Kepler field following her career like a shadow. It is worth pausing on how unusual this is. A single research paper, built on the patient noticing of amateur volunteers, turned an anonymous point of light into one of the most closely watched stars in the sky. Telescopes around the world would soon be pointed at it. So would a great deal of speculation. But before any of that, there was only the data and the question of what could possibly produce it. So let us look at what the measurements actually show, because the strangeness is in the specifics. Over Kepler's 4 years of watching, this star flickered and dimmed hundreds of times in fluctuations large and small, but 2 episodes stand out. Around the 792nd day of the mission, the star's light dropped by about 15%, then came back. And later, around day 1500, there came not a single dip, but a whole complicated cluster of them, a series of dimmings tangled together, the deepest of which swallowed roughly 22% of the star's light. Sit with that number for a moment. Nearly a quarter of the star gone, and then returned. To feel why that is so strange, you have to know what a normal transit looks like. When a planet crosses a star like this one, it blocks at most about 1% of the light. A planet the size of Jupiter, a giant, the largest kind we expect to find, might manage 1 or 2%. That is the ceiling. A 22% dip is not a planet, and it is not even close. To block that much light, whatever passed in front of the star would have to cover something like half of the star's visible disk. There is no planet that large. There is no planet anywhere near that large. And it was not only the depth, it was the disorder. A planet's transits are metronomic. Same depth, same duration, same interval, over and over, because the planet is a solid round body on a fixed orbit. The dips of Tabby's star were none of these things. They were aperiodic, meaning they kept no schedule. They were asymmetric, meaning the star would fade and recover in lopsided shapes rather than the clean symmetric notch around planet calves. They varied in depth and in length, some lasting hours, some lasting days. And taken all together, across 4 years of continuous watching, the dimming occupied less than about 5% of the time. The star spent most of its life perfectly normal, and then, at no predictable moment, it would dim, and dim wrong. A single solid object on an orbit could not do this. The depth ruled out a planet, and the lack of any repeating period ruled out a single orbiting body of any kind. Something else was passing in front of this star, something large, something uneven, and something nobody could immediately name. Now we come to the part everyone remembers, and it deserves to be told carefully, because the careful version and the famous version are not quite the same. Among the scientists who took an interest was Jason Wright, an astronomer at Penn State. Wright and his colleagues had been thinking in a serious and methodical way about how one might actually search for evidence of an advanced civilization around another star. Not little green men, but the large-scale traces that an enormous engineering project might leave in the light. There is a long-standing idea in this field, going back to the physicist Freeman Dyson, that a sufficiently advanced civilization might build vast structures around its star to capture its energy. Not a single solid shell, which the physics won't allow, but a great swarm of separate collectors. A Dyson swarm. If such a thing existed, it would block starlight in irregular, non-repeating ways as the pieces moved across our line of sight. Which is, of course, more or less what Tabby's star appeared to be doing. So Wright and his colleagues raised the possibility in print that the dips were consistent with what we might expect from such a structure. And here is the crucial thing, the part the headlines tended to leave out. They raised it as a last resort. Wright was emphatic, then and afterwards, that the natural explanations had to be exhausted first, that this was a hypothesis of last appeal, the thing you consider only when ordinary physics has been pushed to its limits and still falls short. It was framed as a thought experiment, a way of asking what we would even look for, not as a claim that anyone had found aliens. The world did not hear the caveat. In October of 2015, the story broke loose. The most mysterious star in the galaxy. The alien Megastructure star. The careful conditional clauses fell away, and what remained was the irresistible image of some titanic artificial thing orbiting a distant sun. It became, for a while, one of the most talked about objects in astronomy, not because any scientist had concluded anything, but because the question had been asked aloud, and the question alone was extraordinary. To the credit of nearly everyone involved, the response was not to argue about it. The response was to test it. Because long before the megastructure made headlines, astronomers had a list of natural explanations, and those are the ones most of them genuinely favored. None is tidy. Each fits some of the evidence and stumbles on the rest. That is exactly why the case stayed open. The leading idea, and the one in the original paper, is comets. Not one comet, but a great swarm of them. A family of comets that had broken apart into fragments, strung out along a long, stretched, eccentric orbit, each piece trailing dust and gas. As that ragged procession passed in front of the star, it could block light in deep, irregular, non-repeating ways, exactly the kind of disorder Kepler recorded. Comets are flimsy, dusty, and unpredictable in just the right manner. The trouble is the sheer quantity. To dim a star by anything like 22%, you would need a staggering number of comets, an implausibly large swarm, more than seems reasonable to assemble around one ordinary star. The shape of it fits well enough, but the numbers just don't quite add up. A second idea is dust, not comets specifically, but an uneven ring or cloud of fine dust orbiting the star, thicker in some places than others, so that the star dims as the denser patches drift across. Work using NASA's Spitzer and Swift telescopes, including a study led by Huan Meng in 2017, pointed in this direction, toward circumstellar material, dust close in around the star as the source of the dimming. A third possibility is that the star itself is doing something we don't fully understand. Some intrinsic variation in its own output, an internal behavior rather than an external object. Stars are not perfectly steady, and this one may have moods we cannot yet model. And there were stranger natural candidates still. In 2019 came the suggestion of a plunet, an inelegant name for a genuine idea. A moon torn loose from its planet and slowly evaporating as it orbits the star, shedding material that could account for the dimming. There is also a quieter, longer-running argument about whether the star has been slowly fading over a much greater span of time. In 2016, the astronomer Bradley Schaefer examined old photographic plates of this patch of sky, going back to the late 19th century, and argued that the star had dimmed gradually over about a century, on the order of a sixth of a magnitude across 100 years. Others, including Michael Hipker and Daniel Angerhausen, pushed back hard, arguing that the apparent fade was an artifact of the old plates and the way they were calibrated, not a real change in the star. Kepler's own data did suggest a slow, gradual dimming over the mission, layered underneath the sharp, short dips, so there may be more than one thing going on at once, on more than one timescale. Taken together, that is about where the science sits, a handful of reasonable explanations, none of them complete. So, the telescopes turned, and they did two things. They listened, and then they waited. The listening came first, and it was aimed squarely at the most dramatic possibility. If there were a technological civilization around this star, it might leak radio signals or beam them deliberately. Late in 2015, the SETI Institute pointed the Allen telescope array at KIC 8462852 and listened for artificial radio signals. It heard nothing unusual, no narrow engineered transmission, nothing that nature could not explain. In 2016 and 2017, the Breakthrough Listen project brought the Great Green Bank telescope to bear, searching for narrow-band technosignatures, the telltale radio whistles that natural processes do not produce. Again, nothing. Searches across the radio spectrum, and some looking for pulses of laser light as well, came up consistently empty. This is not proof that nothing is there. Absence of a signal never is. But every place anyone looked for a message, there was only silence. The waiting was the harder and, in the end, more rewarding part. Kepler had moved on. Nobody was watching this star closely enough to catch a dip while it was happening and study the light in detail as it dimmed. So in 2016, Boyajian did something unusual for an astronomer. She turned to the public again, the same public that had found the star in the first place, and ran a Kickstarter campaign to fund a year of dedicated monitoring. More than 1,700 backers pledged over $100,000. It bought time on the Las Cumbres Observatory's global network of telescopes, a string of instruments around the world that could keep the star in view almost continuously. The watching began in March of 2017, and in May, it paid off. The telescopes caught a fresh dimming as it unfolded in real time. The team nicknamed it Elsie, a small pun on LC for Las Cumbres. More dips followed through that year, and they were named with a kind of affection, Celeste, and then Skara Brae and Angkor, after ancient lost places on Earth. These new dips were modest, only 1% or 2 deep, nothing like the great plunges Kepler had seen. But this time, for the first time, astronomers were watching closely enough to measure not just how much the star dimmed, but how it dimmed across different colors of light. And in those colors lay the clue everyone had been waiting for. The star did not fade evenly. Blue light dimmed more than red light. This sounds like a small technical point, and it is the most important single result in the whole story. An opaque solid object, a planet, a slab, a piece of an engineered structure, would block all colors equally. Stand something solid in front of a lamp, and it dims the lamp the same amount whether the light is red or blue. But fine dust does not behave that way. You have seen this yourself on a hazy evening, when fine dust and haze hanging in the air scatter the blue out of the sunlight and let the sun go down deep and red. Small grains of dust do the very same thing here. They scatter blue light more strongly than red, and let the red slip through. So if blue dims more than red, the thing passing in front of the star is not solid. It is dust, fine, small-grained dust. That result, published by Boyajian and her colleagues in 2018, did something the radio silence could not. It didn't merely fail to find a structure, it positively pointed somewhere else. Whatever is dimming Tabby's star, the color of the dimming says it is made of dust, not of metal, and not of anything solid. So where does that leave the most mysterious star in the galaxy? It leaves it, fittingly, as a star surrounded by dust. The consensus now leans toward circumstellar material, an uneven cloud of fine dust, perhaps shed by disintegrating comets or other crumbling bodies orbiting the star, as the best overall fit to what we see. The megastructure was always a last resort, and the color of the light has, for all practical purposes, closed that door. No solid object dims a star blue first. The searches for signals heard nothing. The weight of the evidence has settled quietly on natural dust. And yet, the case is not closed, and it would be dishonest to pretend otherwise. Because no single model reproduces everything. The dust explanation accounts beautifully for the gentle, color-dependent dips caught in 2017. It accounts well for the long, slow fading. What it still struggles with is the original problem, those deep, ragged, irregular plunges that Kepler recorded, the 15% and the 22%, the disordered cluster around day 1500. The comet swarm needed to produce them remains uncomfortably, implausibly large. We have a leading explanation that fits most of the picture and still leaves the hardest part not fully explained. And that, in the end, is where it honestly stands. Not aliens. The evidence never supported that and now actively argues against it. But not a clean, finished answer either. A faint F-class star in Cygnus, ordinary in nearly every way, that dims in a manner we can describe in great detail and still cannot completely account for. It was found by volunteers looking carefully at a graph. It was named for the scientist who took it seriously. It set the world briefly talking about megastructures, and then, under closer watching, told us patiently that it was wrapped in dust. The telescopes are still on it. The star goes on dimming now and then on no schedule anyone can predict. Keeping for the moment the small part of its secret it has not yet chosen to give up. Of all the explanations on the table, a cloud of broken comets, a ring of dust, or something we haven't thought of yet, which one do you find most convincing? Leave your verdict below before we close the file, and that is where we leave file 4 for tonight. Thank you for spending this quiet hour in the archive. If you enjoyed this case file, a like and a subscribe genuinely help the Institute grow, and turning on notifications means the next file finds you the moment it opens. The lamps will stay lit, and the Institute will be here whenever you wish to return. Until then, rest well.